Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about projections of the planes. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now here we are required to evaluate the projections of the oblique plane which happens to be inclined to the vertical plane as well as the horizontal plane. So here we have got an isosceles triangular lamina ABC which is having its base as 40 millimeter long and the altitude of the isosceles triangle has been provided to us as 60 millimeter. So please check, we have not been provided with the length of the isosceles edges of this particular triangle. Rather, instead of that, we have been provided with the altitude of this isosceles triangle as 60 millimeter. Now, the base or the shorter edge AB of this isosceles triangular lamina, it is located in the vertical plane, and it is located in the vertical plane in such a way that when we draw the front view, it is viewed as an equilateral triangle of side 40 millimeter. That is, when we are going to incline this isosceles triangle with respect to the vertical plane, the longer isosceles edges of this particular triangle ABC, they will get foreshortened in the front view because of the inclination of this particular isosceles triangle with respect to the vertical plane. So therefore, there will be foreshortening of the longer isosceles edges of this particular triangle as viewed in the front view projections over there. So therefore, since this particular triangle, it happens to be inclined with respect to the vertical plane to begin with, so as a first instance, we are going to locate this isosceles triangle into the vertical plane. And once we locate this triangle into the vertical plane, so we are going to obtain the true shape projections of this particular isosceles triangular lamina onto the front view projections, which will be obtained onto the vertical plane projections over there. So this way we are going to get the edge view projections onto the XY reference line as projected onto the horizontal plane. The reason is because we have discussed that the shorter edge of this particular triangle, it is located in the vertical plane. So to begin with, whenever we are going to assume that this triangle is going to be located into the vertical plane, so the top view of this particular triangle will be yielding us with the edge view projections in the top view, and these edge view projections will be obtained onto the XY reference line. And further, the edge which is parallel to the vertical plane or contained by the vertical plane, so this is further inclined with respect to the horizontal plane at an angle of 45 degree. So we are required to draw the projections of this oblique lamina which happens to be inclined with respect to the vertical plane in the first instance, and then it is further inclined with respect to the horizontal plane. So let us first of all evaluate the orientation of this particular isosceles triangular lamina into the vertical plane. Now, if we draw this particular orientation of the isosceles triangle, so we'll see that the base, it happens to be 40 millimeter, while this altitude, that is perpendicular distance from this corner of the triangle onto the base, so this will happen to be 60 millimeter. Now, if we draw the triangular lamina into this orientation, we will find that the moment we tilt this particular triangular lamina with respect to the vertical plane, so then we will find that it will be resting with one of its corners into the vertical plane. So none of the edges of this particular triangular lamina will be located into the vertical plane. And further, even when we incline this, so we are going to get foreshortening of all the three edges. We are not going to get the equilateral triangle of 40 millimeter edge upon rotation of this triangular lamina with respect to the vertical plane. So we have to locate the triangular lamina into the vertical plane in this orientation. Now we can see these are two isosceles edges, that is this edge, it is equal to this edge, and now this edge, that is the shorter edge of this particular triangle, this is going to lie into the vertical plane. Now if we rotate this triangular lamina with respect to the vertical plane and we move it through this corner, so this corner will be moved ahead of the vertical plane. Now upon the inclination of this triangular lamina with the vertical plane, we will find that this edge, it is still contained by the vertical plane or parallel to the vertical plane. So this shorter edge or the base of the triangle, this will remain as true length projections in the front view projections over there. And these two longer edges of the isosceles triangle, by virtue of being inclined with respect to the vertical plane, so we are going to obtain the foreshortening or reduction of the length of these longer edges of this isosceles triangle, which will be viewed onto the vertical plane in the front view projection. So upon reduction, we are going to get apparent length of this edge and apparent length of this edge being reduced to 40 millimeter from the true length. So once we obtain these two edges reduced as 40 millimeter projected onto the front view projections, so based upon this orientation, now we will be able to obtain the angle of inclination of this triangular lamina with respect to the vertical plane over here. So this way, this is the orientation which will be appropriate to evaluate the projections of this isosceles triangular lamina ABC, which is inclined with respect to VP and then with respect to HP. And once we obtain the equilateral triangular projections in the front view, then this edge, which happens to be true length contained by the vertical plane, thereafter in the second iteration, so this edge, vertical edge of the triangular lamina, that is the shorter edge, so this will be further inclined at an angle of 45 degree with respect to the horizontal plane. So this way we are going to evaluate the projections of this isosceles triangular lamina. Now let us proceed with the evaluation of the orthographic projection. So as we have discussed, since this lamina, it is contained by the vertical plane to begin with, so we are going to get the front view projections onto the vertical plane, which are going to provide us with the true shape projections of this lamina. Now here we have got 40 millimeter, it is the length of the base. So that is, we have to draw this 40 millimeter distance perpendicular to the XY reference line. So A dash B dash, it happens to be 40 millimeter. Now the distance B dash C dash and A dash C dash has not been provided to us. So how do we obtain this? We know that this total length of the base, it is equal to 40. So at a distance of 20 millimeter from B dash or A dash, we are going to find the midpoint of this shorter edge or the base, which is at a distance of 20 millimeter from the ends A dash or B dash. So from this point, we are going to measure this altitude equal to 60 millimeter. So from the midpoint of A dash B dash, we are going to mark this altitude of this triangle as 60 millimeter. So please check, here we have marked this altitude length is equal to 60 millimeter. Once we obtain this altitude length is equal to 60 millimeter, we'll be able to obtain the corner C dash corresponding to this isosceles triangle, and then we can join A dash C dash and B dash C dash. So this provides us with the basic construction of the true shape of this isosceles triangle into the vertical plane, right? Now once we obtain the true shape of this particular lamina into the front view projections, now since this lamina is contained by the vertical plane, so the top view projections of this lamina will be obtained onto the XY reference line. So A dash and B dash points, they are going to coincide with each other as AB into the top view. Similarly, the C dash point from the front view, once we project it onto the top view projections onto the XY reference line, so we are going to obtain the point C onto the XY reference line, because A, B and C points corresponding to the three corners of this lamina, they are contained by the vertical plane. So the top view projections, they have been marked as edge view projections into the horizontal plane over here. Now we have obtained the edge view projections of this lamina onto the horizontal plane. Now usually what do we have in most of the problems? The inclination of this edge view with respect to vertical plane, it is given to us, and accordingly the foreshortening of the edges A dash C dash and B dash C dash, usually it is evaluated. But in this case we have been provided with a situation where we have been provided with this foreshortening effect directly, and using this foreshortening of the edges A dash C dash and B dash C dash over here, we are required to evaluate the angle of inclination of this edge view with respect to the vertical plane. Now we know that once this triangular lamina, it is inclined with respect to the vertical plane, the resultant front view which is obtained, it is an equilateral triangle having edges is equal to 40 millimeter. So now we can draw the front view. Now you can see this distance A1 dash and B1 dash, this is equal to the true length, that is 40 millimeter. So this distance is already available with us. So there is no foreshortening of this edge, because this edge A and B, this edge is contained by the vertical plane. So its projection onto the vertical plane will reveal the true length of this particular edge in the front view. So A1 dash and B1 dash, so this edge of the triangle, it represents the true length. Then we know that because of the inclination of this triangular lamina with respect to vertical plane, so there is foreshortening of the edges B dash C dash and A dash C dash in such a way that after the inclination of this surface of the triangle with respect to the vertical plane, we are able to obtain the apparent length of B1 dash C1 dash is equal to 40 millimeter, and apparent length of this slant edge A1 dash C1 dash is equal to 40 millimeter. So we are able to obtain an equilateral triangular projections of this particular isosceles triangular lamina onto the front view projections over here. Now having obtained the true length projections of this edge A1 dash B1 dash and apparent length projections of the edges B1 dash C1 dash and A1 dash C1 dash, now we are going to obtain the angle of inclination of the surface of this lamina with respect to the vertical plane. So how that can be done? From A1 dash and B1 dash, we are going to draw one vertical projector line. Similarly, from the point C1 dash, again we are going to draw one vertical projector line over here. Now we can see over here that the angle of inclination of the surface of this particular triangle will be evaluated when this true length, that is equal to 60 millimeter, this true length between AB and C points, this is transferred between these two end projectors over here. So A1, B1 projectors will be located onto the XY reference line, while end C will be moved away from the vertical plane. So this distance we know now. So this distance is equal to how much? It is equal to 60 millimeter. So with this as our needle point, we are going to open compass is equal to 60 millimeter and mark an arc onto the vertical projector line which is emerging from the point C1 dash in the elevation. And once we transfer this edge view of 60 millimeter into the inclined surface of this particular isosceles triangular lamina into the plan projection view over here, so we will be able to obtain the angle of inclination of this particular triangular lamina with respect to the vertical plane. And since this is the true length, we can check. We know that the distance between the points A1, B1 and C1 happens to be true length. So this way the true length has been inclined at an angle of phi over here. So that is why the angle phi has been mentioned. So now we know that once we have obtained this particular rotation of the surface of the lamina at an angle phi with respect to vertical plane. Now we also know that the edge which is contained by or parallel to the vertical plane, it is further inclined with respect to the horizontal plane. So this is the true length we can check. And A1 dash C1 dash, it is the apparent length. B1 dash C1 dash, it is also the apparent length. But A1 dash B1 dash, it happens to be the true length in this isosceles triangle front view projections over here. So now this edge which is parallel to the vertical plane, it is further inclined at an angle of 45 degree with respect to horizontal plane. So now we have marked a projection line which is inclined at an angle of 45 degree with respect to the horizontal plane. So alongside this orientation line or the projection line, the points A1 dash and B1 dash, they will be located over here. That is A2 dash and B2 dash points, they will be located alongside this particular orientation projector line which has been drawn at an angle of 45 degree with respect to the horizontal plane. So now we are going to mark two arcs equal to the radius 40 millimeter. So from this point, mark an arc 40 millimeter. From this point, mark an arc equal to 40 millimeter. So wherever these two arcs, they are going to intersect with each other, we are going to obtain the point C2 dash over here. So now you can check, this is A2 dash, this is B2 dash. So this distance happens to be 40. So this way, the front view projections of the oblique triangular lamina inclined to VP and HP, they have been obtained. Now the corresponding projections in the top view we are going to obtain. So in order to obtain the corresponding top view projections of this particular triangular isosceles lamina, so now corresponding to this isosceles triangular lamina, we are going to draw vertical projectors through the 3 points A2 dash, B2 dash and C2 dash into the plan projection view, and also draw the horizontal projectors through the plan projection points of the previous view A1, B1 and C1. So wherever we obtain the intersection of the corresponding points, so we will be able to obtain the location of the points A2, B2 and C2 in the top view projections over here. Now we can check. We have drawn the vertical projector through the point A2 dash, B2 dash and C2 dash over here. Now we have to draw the horizontal projector through A1 and B1. So once we draw the horizontal projectors through A1 and B1, so we see that at point this, that is, we are going to obtain intersection of vertical projector of A2 dash and horizontal projector emerging from A1. Similarly, at this point, we are going to obtain intersection of vertical projector drawn through B2 dash and horizontal projector drawn through point B1 in the previous plan projection view. And finally, once we draw the horizontal projector through C1, so we'll see that this horizontal projector drawn through C1, it intersects at this point with the vertical projector which has been drawn through the point C2 dash in the front view. So the A2, B2 and C2 points of the top view projection of this oblique lamina have been evaluated. Now we can join points A2, B2 and C2. So this way, so this is the front view projection, A2 dash, B2 dash and C2 dash. This is the top view projection, A2, B2 and C2 of the oblique isosceles triangular lamina, in which the surface of the lamina, it is inclined with respect to the vertical plane at an angle phi, and the true length of the base or the shorter edge of this isosceles triangle, it happens to be inclined with respect to horizontal plane at an angle of 45 degree. So this is all for today. So I hope that through this discussion you would have understood about the procedure, how do we evaluate the orthographic projections of this isosceles triangular lamina, which happens to be inclined with respect to vertical plane as well as the horizontal plane. So we will be continuing with further discussion regarding few more illustrative cases of the orthographic projections of the oblique planes in the coming lectures. So thank you very much. Thanks a lot.